2019 August past paper question. Show that the center of mass of a thin uniform semicircular wire of radius A is at a distance 2a over pi from its center, and a thin uniform hemispherical shell of radius A is at a distance a by 2 from its center. A spoon is made by rigidly fixing to a thin uniform hemispherical shell of center O and radius 2a. A thin handle ABCD made of uniform wire consisting of a straight piece AB of length 2 pi a and a semicircular piece BCD of a radius A such that the diameter BD is perpendicular to AB as shown in the figure. The point A lies on the rim of the hemisphere. OA is perpendicular to AB and OD is parallel to AB. Also, BCD lies in the plane of OABD. The mass per unit area of the hemisphere is sigma and mass per unit length of the handle is A sigma by 2. Show that the center of mass of the spoon lies at a distance 2 over 19 pi into 8 pi minus 2 pi squared minus 1 into A below OA, and a distance 5a over 19 from the line passing through O and D. The spoon is placed on a rough horizontal table with the hemispherical shell surface touching it. The coefficients of friction between the hemispherical surface and the table is 1/7. Show that the spoon can be kept in equilibrium with OD vertical by a horizontal force applied at A in the direction of AO. Solution for this question. First part. The first one, a thin uniform semicircular wire of radius A. Finding center of mass of a semicircular wire. Consider a semicircular wire with radius A and mass per unit length rho. This is one of the semicircular wire, radius A, mass per unit length rho. Center for the OX axis, this is the Y axis. Mass of semicircular, this one circumference is a pi A, therefore mass pi A into rho. Pi A into rho. Center of mass from point O is the X bar. Symmetrically, the center of mass will be in the OX axis. Therefore, from might be here anywhere. Therefore, center of mass from point O is X bar. Consider a small piece of wire at an angle theta from the OX axis, because we are going to divide this circular wire as so many small pieces of wire. So one piece of wire, consider one piece of wire at an angle theta. So angle theta, at theta you consider one of the small piece of wire, the red color, but not the big like this one. You want to consider this one very small. the red color portion, wire, a small piece of wire at an angle theta we consider. Let this piece makes an angle delta theta at the center of. So delta theta is a very small angle. About this piece make an angle delta theta at the center of. Not a small one. When the piece of wire is small, very small, the delta theta also very small. So big. That is all very small. That is why we mention the angle delta theta, small angle. Length of this piece, we already learned from our theory in trigonometry. Length of this piece, this one A, this angle delta theta, therefore this length of red color small wire is A delta theta. Mass of this piece, length is A delta theta, mass per unit length is mass per unit length rho, therefore length of this small piece A delta theta into rho. A delta theta rho. A rho into delta theta. Center of mass from point O, this one, A cos theta. The center of mass here, therefore from the point O, that is the distance at A cos theta from point O. Now we are going to make this semicircular wire by considering so many small pieces. We make one of the table. So body is a mass, distance of center of mass from point O. Element, here small element is a small piece of wire. Mass of the small piece of wire A rho delta theta, and distance of center of mass from point O, you already A cos theta. You have A cos theta. And next body is our full wire, circular wire. Mass of this circular wire here, pi A rho. Pi A rho. And the distance of center of mass, that is the x bar, we want to calculate. Using the principle of moments about the OX axis, this is the, consider the wire, this is the mass, pi A rho into distance x bar is equal. Now we are going to consider all possible small elements. So one of the elements, this one. So mass of this one A rho delta theta into distance A cos theta. This is for one element. The moments for the one element. A rho delta theta into A cos theta. So we want to consider all elements. Therefore we want to add. That's here we do integrate. Means for all elements. This all elements possible from theta varies from minus pi by 2 plus pi by 2. So it comes here, there. Therefore small, this range minus pi by 2 plus pi by 2. When we simplify, pi A rho x bar is equal, this one, A into A squared rho cos theta into delta theta. For integration, we can consider delta theta as a d theta. Integrating limit minus pi by 2 plus pi by 2. Our x bar is equal A over pi into because draw cancel both sides. Here a pi might come here. A over pi into integration minus pi by 2 plus pi by 2 cos theta into d theta. Now we know the integration a over pi into, when we integrate cos theta, that is sin theta, limit minus pi by 2, pi by 2. This is a over pi into sin pi by 2 minus sin minus pi by 2. Sin minus theta, we know minus sin theta. Therefore this one, this term minus sin pi by 2. Minus into minus, here plus. Therefore this one a over pi into sin pi by 2 plus sin pi by 2. A over pi into this one 1, 1 plus 1, 2. 2a over pi is the x bar. Semicircular wire radius a is at a distance 2a over pi. This is the question, 2a over pi. So we proved it 2a over pi from its center. Now we want to consider the second things. The uniform hemispherical shell. Finding center of mass of hemispherical shell, radius a, mass per unit area sigma, this is one of the hemispherical shell with center O. Mass of this hemispherical shell. So we want to find out the total surface area, full sphere, that is a 4 pi r square. This is a hemispherical, therefore 2 pi a square. The surface, curved surface, 2 pi a square. When multiplied by sigma, that is the mass of this hemispherical shell. Therefore 2 pi a squared into sigma. 2 pi a squared into sigma. This is the x-axis through O, horizontal. This is the y-axis. By symmetry, center of mass G lies on OX axis. It is obvious. Center of mass might be along this OX axis. OG is equal x bar, let's say. Now we are going to divide this hemisphere into so many rings parallel to y-axis. Consider one of the ring at an angle theta. This is one of the ring, angle theta. We divide this hemisphere as so many rings. From here, theta is at 0 to pi by 2 range. We divide this as so many rings. 0 to pi by 2 theta variety. So one of the ring at an angle theta. Consider next ring at an angle delta theta. One more ring, angle delta theta. Very close to this one. Next ring at angle delta theta. This is a very small angle. That is why we mention as a delta theta. Next ring. So what is the shape of this ring? These two rings, this is one of the rings here, these two rings approximately make a hollow cylinder, as delta theta is very small. If delta theta is very small, it is possible to consider as a hollow cylinder. Height of the cylinder, the height of the cylinder, this is the height of the cylinder, this one. This is the height of the cylinder. What is this height? A into delta theta. This one. The height of the cylinder A into delta theta. This is considered as a small element. So now here small element is the cylinder. By assembling so many cylinder, hemispherical shell is made. Radius of these cylindrical elements. So radius of the cylindrical element is this distance. This one, what is this? A sine theta. Area of this element. Oh, we know the area, curved surface area of a cylinder of 2 pi RH. 2 pi into radius into height. Therefore, area of this element 2 pi. We already know the 2 pi into A sine theta into height A delta theta, 2 pi RH. So mass of this element, this area should be multiplied by mass per unit area. Mass per unit area is sigma. So mass of this element should be multiplied, this quantity should be multiplied by sigma 2 pi A squared sin theta delta theta into sigma. This one 2 pi A squared sigma sin theta into delta theta. Center of this element from O. Center of mass of this element from O, that is A cos theta. So now we do consider this hemispherical shell as an element, as a so many element. Body, mass, distance of center of mass from O, hemisphere, mass of this hemisphere 2 pi A square sigma. First one here, 2 pi A square sigma. 2 pi A square sigma. Distance of center of mass from O, let's say x bar, we want to calculate. Then small element, as a cylindrical, the mass of this small element cylinder 2 pi A square sigma sin theta delta theta, and center of mass A cos theta. A cos theta. Using the principle of moments, mass into center of mass for the hemisphere, that means 2 pi A squared sigma into x bar is equal. Now we want to take all moments of this element. So the moments of this small element, this mass into this distance. 2 pi A square sigma sin theta delta theta into A cos theta. Now we want to consider all possible small elements. That means all possible small cylinder. So cylinder is possible from, as we already know, 0 to the first cylinder might be here at an angle 0. Then the last one cylinder is possible at an angle pi by 2. Pi by 2. Therefore, now we want to integrate which range? Minus 0 to pi by 2. Two pi a squared sigma into x bar is equal pi a squared into a cube sigma into 0 to pi by 2 integrate 2 sin theta cos theta into d theta delta theta as a, we put as a for d theta 2x bar, some other terms cancel, a into integration 0 to pi by 2 sin 2 theta, double angle identities, minus, now we want to integrate sin 2 theta. When integrate sin 2 theta, that is minus half cos 2 theta. Therefore, this one minus a by 2 cos 2 theta, limit 0 to pi by 2. And substitute minus a by 2 into cos pi for the theta pi by 2. Therefore, the 2 theta pi minus theta 0, cos 0. Minus a by 2 into cos pi minus 1 and cos 0, 1. This one minus 1, minus 1, minus 2, minus into minus, plus 2 cancel, therefore a, therefore x bar is a by 2, this one. Question. A thin uniform hemispherical shell of radius a is at a distance a by 2 from its center. A by 2, we proved it. Okay, now we come to our problems. Spoon. The spoon is made by the spoon, hemispherical shell of center O and a radius here 2a, radius 2a, and this is the thin handle, so the thin handle made one of the small circular, semicircular piece and a straight piece. So D. Let the center of mass of spoon is x bar, y bar. We don't know, therefore this center of mass x bar, y bar. From here, this x is x bar, here y bar. Okay, now we consider all possible elements to make this spoon. Body, what are the body used to make this spoon? Mass, center of mass from OD, center of mass from OA. So the first body, this one, semicircular wire. Semicircular piece, this one. This one, BCD, radius A. Mass of this one, pi a squared sigma by 2, because we are given mass per unit length. Mass per unit length of the handle is a sigma by 2. Therefore, this mass we want to find out. What is this length? Pi a. Full circle 2 pi a. Therefore, semicircle pi a into a sigma by 2. Pi a into a sigma by 2. Well, pi a into pi a into a sigma by 2. Yeah. A sigma by 2. So here A squared pi A squared sigma by 2. And center of mass from OD. From OD, center of mass. Center of mass here, no? So from OD, this is the distance A. And center of mass from OA. This distance, we know the A by 2. This distance 2A over pi. This distance 2A over pi. And this distance 2 pi A. We have 2A over pi plus 2 pi A. Center of mass, this red color point, from OA. Next, we consider the straight portion AB. This length 2 pi A, therefore mass of this length of this straight portion AB is equal to 2 pi A into A sigma by 2. Mass per unit length A sigma by 2. Therefore this one 2 pi A into A sigma by 2. Then pi A squared sigma. Center of mass from OD, the center of mass from OD is the 2A. And center of mass from OA, this one, half distance, full distance 2 pi A, therefore this one pi A. The next portion, this hemispherical shell. Mass of this portion 2 pi A squared, but here 2 pi A squared is the surface area, but radius is 2A, therefore 4 pi A squared, 2 pi A squared into 2A whole thing squared, 8 pi A squared into mass per unit area sigma, 8 pi A squared sigma. Center of mass from OD, this one OD, for center of mass from OD is a 0. And center of mass from OA, from this OA, this one, we will identify A by 2 distance, half of the radius. Here radius is a 2A, therefore this distance is a A. But below this level, below O axis, therefore that is mentioned minus A. Now spoon. So what is the mass for this new spoon? We want to add all these three elements. This one plus this one plus this one. That is the total mass of the spoon. Pi A squared sigma by 2 plus pi A squared sigma plus 8 pi A squared sigma. This one 9 pi A squared sigma plus this one. Therefore 19 pi A squared sigma by 2. And center of mass from OD and OA X bar, and this one minus Y bar below this level, below this OA. Principle of moments about OA. Now we consider about this or this one. Principle of moment for this one. First one, (19 pi A squared sigma A by 2) into this one. for the full body, this one. This mass into this distance. 19 pi a squared sigma by 2 into minus y bar is equal, for this first one, this one. This mass into this distance. Pi a squared sigma by 2 into 2 pi a plus 2a over pi. This one, semicircular portion, plus then for this one, this mass into this distance. Pi a squared sigma into pi a. Pi a squared sigma into pi a. Then for this portion, this mass into this distance. 8 pi a squared sigma into minus a. Minus a. When simplifying this one, we have to be very careful to simplify this one. A squared sigma is cancelled from both sides. A squared sigma. Therefore, here rest in pi a squared sigma. Pi a squared sigma cancel. Here pi a squared sigma, pi a squared sigma, pi a squared sigma, pi a squared sigma cancel. Therefore, rest. Here, this one minus 19 by bar by 2 is equal. Here, this one pi by 2, when multiply this one, pi by 2 into 2 pi a, so cancel, yeah, pi cancel, therefore 2 and 2 cancel, therefore this one pi a, and simplify this one, 2 and 2 cancel, therefore a over pi, and here is pi a, and here plus 8 minus a, therefore minus 80. This one multiply by minus 19 by bar by 2 is equal 8a, multiply by minus, no, here 8a, pi a, 2 pi a, therefore minus 2 pi a minus a over pi. Therefore 19 by 2 into y bar is equal a over pi is the common factor. Therefore within brackets 8 pi minus 2 pi squared minus 1. Therefore y bar 2 over 19 pi within bracket 8 pi minus 2 pi squared minus a minus 1 into a. That is one. Show that the center of the spoon lies at a distance 2 over 19 pi. This one below OA. Now we want to find out the other distance from OD, passing through OD. This one. Or in the chart, the table, now we want to consider this one, this distance from OD. And also we can find out this x bar. This mass for this one, this mass into this distance is equal, this mass into this distance plus this mass into this distance plus this mass into this distance. I will explain well. This mass into this distance is equal this mass into this distance plus this mass into this distance plus this mass into this distance. Therefore here, principle of moments about OD. 19 pi a square sigma by 2 into x bar. This one, 19 pi a square sigma into x bar is equal. Next one, pi a square sigma by 2 into a. Pi a squared sigma by 2 into a. Then pi a squared sigma into 2a. Then 8 pi a squared sigma into 0. Next one, pi a squared sigma into 2a plus 8 pi a squared sigma into 0. Yeah, when we simplify this one, pi a squared sigma cancel from both sides. Therefore, here rest 19 by 2 x bar. 19 by 2 x bar is equal pi a squared sigma cancel. Therefore, this one a by 2. Here, this term 0. Therefore, here 2a. Therefore, this one 19 by 2 x bar is equal a by 2 plus 2a, 5a by 2. Therefore, x bar is equal 5a over 19. This part. Distance 5a over 19 from the line passing through O and D. Now we use this part. The next part, spoon is placed on a rough horizontal table of mu is equal 1/7. Okay. This is one of the spoon. Now is placed on a horizontal table. Weight acts at the center of mass. Where is the center of mass? We already find it. The center of mass here. From OA to this distance, from OM to this distance, the center of mass. Therefore, in this position, it is not possible for the equilibrium in this position. Therefore, definitely this position may be like this one. Be here like this one. The center of mass for the balance. Not possible for this way. It can't. Or not possible for this also, not possible. Have a center of mass in this right side. Much weight, no. Therefore, definitely possible like this one. This is the position. So, to keep this in a perpendicular, to keep this one by applying some of the force, so that the spoon can be kept in equilibrium with OD vertical. Now we want to keep this as an OD vertical. This one OD, no? OD, this one, OD. This OD. Not vertical now. By giving some force, we keep this as OD vertical. Therefore, now we give one of the horizontal force. By giving a horizontal force, that the equilibrium is possible when a horizontal force P is applied at point A. by this force, by applying a horizontal force at P, it is possible for the equilibrium with OD is a vertical. By applying this force. Denote frictional and normal reaction force on this diagram. How it will going to slip this way. Now by using this applied force, therefore the frictional force might be in this direction, opposite to this direction. And the normal reaction at this curved surface by a table through H, that is R, the normal reaction. For the equilibrium of spoon, resolve the forces horizontally. For the equilibrium, resolve horizontally, F is equal P. Resolve vertically, vertical forces. What are the vertical forces? R is equal W. This distance 2A. Therefore, now we want to take a moment about point H. So, what are the forces coming? Only this P and W. W in this direction, P opposite direction. Take a moment about H, two forces W and P. Therefore, W into taking moment point H, therefore W into this distance X bar. W into X bar is equal F into P into from this distance radius 2A, P into 2A. W into X bar, we already find the previous part as a 5A over 90 is equal to PA. Therefore, P is equal 5W by 38. Applying force at point A to keep OD is vertical. So what is the F? What is F? F is equal already P, no? Therefore F also this one, 5W by 38. 5W by 38. This frictional force F is equal 5W by 38 and normal reaction R is W. Consider F over R. F over R is equal, for the F 5W over 38, R is equal W. F over R is equal 5 over 38. F over R is equal 5 over 38. Okay, now we do some small obvious statements. 35 less than or equal less than 38. Therefore, 1 over 35 greater than 1 over 38, reciprocal inequality. So 5 over 35 greater than 5 over 38. So when simplify this one, 1 over 7 greater than 5 over 38. When substituting for 1, 7, we can put mu. Because we are given the coefficient 1, 7. The coefficients of friction between the hemispherical surface and the table is 1 over 7. That means mu is equal 1 over 7. For this 1 over 7, I can put mu. And for this 5 over 38, have a look, the 5 over 38, I can put F over R. Therefore, for this here, 1 over 7 mu, 5 over 38 F over R. Therefore, mu greater than F over R. Therefore, hence the spoon can be kept in equilibrium. Equilibrium is possible at this position by applying a horizontal force so that OD is vertical. Mu greater than F over R. Hence, the spoon can be kept in equilibrium.